On this computer. I hope everyone's having a good start to their morning. I've got my coffee, walked my dogs. One of my dogs went ahead and kicked the day off right and peed inside. But, you know, we had just gone on a walk, so that would be the perfect time to do it. Um, at any rate, last time we were talking about, yep, last time we were talking about thermodynamics, and specifically what we were talking about was the Gibbs free energy equation. And with respect to the Gibbs free energy equation, we looked at a graph um, and a table that showed whether or not a reaction is going to be spontaneous or non-spontaneous. And this was, I liked this graph because I like this graph and this table because of the fact that it's communicating the same message, but it's taking slightly different looks at it. You know, at the end of the day, this equation right here is what you need to know. Um, with that equation, there's a couple of things that you can kind of recognize. One of which is that delta G must be negative in order for a reaction to be spontaneous. It's positive if it's not. Now, personally, this table right here and this series of graphs right here, um, it's something that I have a pretty good sense of, but what's easiest for me to do is give myself specific numbers. And so what I mean by that is if you're confronted with a question that says, under what circumstances is delta G negative? What I think is helpful is to plug in actual numbers and say, okay, well, if delta H is 15 and T equals 5 and delta S is negative 300. Okay, what's my delta G going to be? Okay, well, what I'm going to do is I'm going to say 15, or sorry, not equals, 15 minus 5 times negative 300. Okay, so we're at 15 minus, that would be negative 1500. Okay, so that's effectively 15 plus 1500. So in this case, my answer is 1515, and therefore my delta G is positive, and therefore this is a non-spontaneous situation. I'm going to say non-spont to save myself the stress of writing all those letters. So essentially that's what I'm getting at is with or what we're trying to communicate and convey with these two tables. What are the circumstances where delta G is negative? What are where it's positive? Is it an increase in or is it a release of energy? Is it energy absorbed? So what I would recommend doing is making sure that you know, first and foremost, delta G is negative or positive. What does that mean? Then go on and say, okay, well, what if delta H is positive and the product from negative T delta S is also positive? What does that mean? Well, that means delta G is also positive. And then this table right here just communicates it in slightly different ways by basically presenting you with specific approximations of temperature. Won't there be a unit conversion? That's a great question. And so in this case, you know, I just gave you arbitrary numbers. There are absolutely circumstances where your enthalpy change is going to be something in kilojoules, whereas your entropy change might be in joules. And so that is one thing to absolutely account for. Great question, Andrew. So make sure that whenever these numbers are presented, like here, this 15 and negative 15, or sorry, negative 300, I didn't include units for that calculation, but anytime you see something like this, if it is 15 kilojoules and this is 300 joules, well, then you have to say 15 kilojoules is 15,000 joules. So make sure that you account for that. That's a great question, then. And a great reminder for everyone. Okay, so I'll go ahead and just say, throw in the chat a thumbs up if this sounds good. And a thumbs down if I'm going to spend a little bit more time on it. Okay, cool. We're getting some good responses there. All right, now what we'll do next is we'll proceed to what information can we get from delta G? I know with the delta G in Gen Chem 2, whenever you started working on that, it became, okay, we're doing this delta G calculation where we're talking about enthalpy and entropy, but what does that mean for a given reaction? Well, one of the things that you can do with the delta G value is you can figure out what reaction or what direction a reaction will go. And so when we talk about this, really what we're meaning is products or reactants. So if we have a reaction that goes A to B, well, given our delta G value, is that going towards B, our product, or is it going towards A, our reactant? Now, if the forward reaction is favorable, then the reverse reaction is unfavorable. So what that means is if you have delta G equals negative 55 for the forward reaction, well, then that's a spontaneous reaction. And so you're going to go in the direction of producing B. That also means that this delta G equals positive 55. So that's a reaction that's unfavorable. And that could be unfavorable due to a decrease in entropy. It could be a result of energy has to be input to this reaction. You don't really know that, and you don't need to know that given this situation. What you do need to know, however, is, well, which direction is it going to go? Now, if the initial concentration of our reactant A is above its equilibrium concentration, okay, so remember that in any given reaction or in every reaction, we're going from A to B. We're going from reactants to products. And we're going to proceed in that direction until we reach equilibrium. So you might have something, so you'll have a reaction that goes A to B, and you might have it really kind of like this. The larger arrow is showing that we are going more towards B than we're going towards A. So the reverse reaction is happening, but we haven't reached equilibrium. And so the reverse reaction is happening at a lower frequency than the forward reaction. So when is that going to be the case? Well, when our initial concentration of our reactant is above its equilibrium concentration. That means we have an excess of A. And since we have an excess of A, we want to make, or let me rephrase that. We want to use A and make B. We want to use up A for the purposes of making B. Now, did somebody just have a question? Okay. So essentially what we've got is this situation right here, where A goes to B when delta G is less than 0. Delta G is less than 0 when delta G is a negative value. Then our B will go to, or our product will go to our reactant when delta G is greater than 0. Now, if the initial concentration of B, our product, is above its equilibrium concentration, then we're going to go in the opposite direction. We're going to proceed toward A. I think that these two statements right here and this idea right here, if you understand that, then I think you're in a very good position to understand equilibrium and reaction. Which direction is it going to go based on the delta G? Now, if the initial concentration when B goes to A when our delta G is less than 0, and A goes to B when delta G is greater than 0. This is always when our initial concentration of B is above the equilibrium concentration. So that's basically what you need to be asking yourself. What is the concentration of my reactant and my product, and what is it at equilibrium? So here's just the visual depiction of that. So this gives us three different scenarios. When our concentration of A and B are at equilibrium, well, then our delta G is 0. When our concentration of A is greater than our equilibrium level of A, which is depicted by this green line, well, then we're going to go towards B, and delta G is less than 0. Now, when B, our product, is in a greater concentration than our equilibrium level, then we're going to go in the reverse reaction towards A when delta G is greater than 0. So essentially, if I were to provide you with or the way that a question would be asked about this would be something like, the equilibrium concentration of this reactant is 2 micromolar. And you have, I'll give you a equilibrium concentrations, 2 micromolar and 1.6 micromolar. So this is the equilibrium situation, or this is the equilibrium, this is where you are at with respect to equilibrium. Now, you can take these values, and something that you've definitely done before in Gen Chem 2 is you can calculate an equilibrium constant. So that KEQ, where you take your product concentration at equilibrium divided by your reactant concentration at equilibrium. Now, if I said in a particular situation, you have an A concentration of 6 micromolar and B equals, let's just say 0.2 micromolar. Well, this one's pretty easy, I think, because you could compare both of these and you say, well, B's concentration is less than our equilibrium amount. A's concentration is way above our equilibrium amount. This is going to proceed by taking A and making more of B. So that's like the direct sort of question about this. It can get a little bit more murky whenever I say something like, well, A has a concentration of 12 micromolar. Okay, that's higher than equilibrium. B is 3.2 micromolar. This is where it's a little bit murkier, and you might think, well, A is higher than the equilibrium concentration, but B is also higher than the equilibrium concentration. So which way is this reaction going to go? And that's where you'd be able to calculate a KEQ. And some of y'all might be thinking, I really wish that I had left KEQ in Gen Chem 2. It's not the biggest part of a biochemistry class, but it's a ratio. And ratios are super important. So in this case, what you'd do is you'd take 1.6 divided by 2, and that would be approximately 0.8. So that's your KEQ, your ratio for this. And what you'd be able to do is then be able to figure out, okay, how much higher is A than B compared to this ratio right here? And then you'd be able to say, okay, well, it's going towards the product because of the fact that our A concentration is 6x and our B concentration is only 2x. So you see a ratio there that it's going to be going towards a product. Okay. Now, we can also get from this useful energy from a reaction. H represents the total energy, S is the wasted energy because of order or disorder, and G represents the useful energy. So delta H is equal to delta G plus T delta S. If the initial concentration of A is above the equilibrium concentration, then the reaction will proceed towards B. So we can calculate, with all of this, the useful energy from a reaction. Now, the amount of useful energy is derived from the reaction is dependent on how far the initial concentration of A is above its equilibrium concentration. So previously we were just talking about, well, which direction is it going to go? But now we're looking at how far A is above. So we're thinking about magnitude. Now, this, I think we got, this is our last slide here. And then we're going to go on to the PowerPoint for today. The free energy change, or delta G, of any reaction is related to the ratio, equilibrium, and non-equilibrium concentration of the products and reactants. Okay. So this is this was a big part of Gen Chem 2. Free energy changes. And for this class, understanding this and understanding delta G values and classifying a reaction as favorable or unfavorable is a very big part of this class. So when you look at this, if you're at all like me and you're thinking back to Gen Chem 2 and you're like, oh, I struggled with that. Well, then I would argue that it's important, but it's not the biggest part of biochemistry. So what we're really looking at is a delta G and how far of a measure it is from equilibrium. So how much we're going to be able to use this. Now, with respect to so we're going to use this, and what we're using it for is our free energy stuff is we're using it for understanding metabolism. Now, this class, Chem 4375, is kind of a precursor for Chem 4385. We're going to get into a little bit of metabolism, and we're going to do it pretty quickly here. So, whenever we talk about our standard free energy change as biochemists, we're talking about delta G naught prime. Delta G naught, if you remember, that was how we looked at a standard free energy change of any given reaction. Now, what we can do is take a delta G value and make it equal to R times T. R is the gas constant, T is the temperature, and ln KEQ is your natural log of your equilibrium expression, or sorry, of your equilibrium constant at standard conditions. So when we think about a standard free energy change or the free energy of a reaction, we can relate it to, with this with this graph right here, the equilibrium constant. So our equilibrium constant is the ratio of our products to our reactants, because KEQ is our equilibrium expression of our product concentration over our reactant concentration. And this can give us like a sense of how far a reaction is from equilibrium and how how favored the products are versus the reactants. So if we have products, so I'm going to say start down here. This is a reaction where products are favored. Let's see, this would be approximately 1,000 to 1 reactant. So if we have a chemical reaction where when you have the reactant present, it's going to so spontaneously and easily go towards the product that it's just such an extremely favorable reaction. And you have a free energy change that is right around here, negative 3,600. So that means that it's, well, one, it's negative, indicating that it's favorable, and negative 30, well, I'll call it like negative 4,000. It's extremely favorable given the magnitude and the value being negative as opposed to positive. Now, if we go over here, we have a KEQ of 0.001. Then what we're looking at is basically one product to 1,000 reactants. At equilibrium. So you set the reactant there, and basically it's not going to budge because the equilibrium is 1,000 of your reactants to one product. So it's going to appear to go very, very slowly because it's not a spontaneous reaction. So up here at this position, we've got highly unfavorable reactions. And that's really the purpose of a graph like this, is to show the relationship between an equilibrium constant and a standard free energy change, where we're basically looking at the favorability of a reaction. And that is all because of this equation right here. Since KEQ is a constant specific for each reaction, then delta G naught is also a constant specific for each reaction. So essentially what we're saying is this graph gives us a way of looking at every single chemical reaction and saying, okay, well, based on the free energy change, what is the equilibrium constant? Or based on the equilibrium constant, what's the free energy change? Because KEQ can be measured experimentally, we have a way to determine that delta G naught. So this is a nice way that you can do that sort of calculation. Now, if KEQ is less than 1, delta G is going to be a positive value. So this right here, this point right here, to the left, these are all KEQ values. I'll just label them as low KEQ values. So low KEQ values indicate unfavorable reactions. So low KEQ means unfavorable. And another perspective on that is high delta G naught indicates an unfavorable reaction. High KEQs, by contrast. So a KEQ of greater than 1. So to the right, this means favorable. Low delta G naught indicates favorable. So if there's something that from this and maybe the past few slides, if there's like, what should I take away from this? What you should take away from this is this idea right here. This concept. What is the magnitude of my KEQ? What is the magnitude of the delta G naught? And what does that mean for reaction spontaneity and favorability? So a favorable reaction is a spontaneous reaction. A spontaneous reaction has a low delta G and a high KEQ. And that's all captured with this equation right here. And here's just another way of looking at some of these things. So RT, so this equation right here, what some folks will do is look at it and say, well, these are under standard conditions, so here's my R value, here's my T value. So I'm just going to plug in 2.48 kilojoules per mole for this number right here, or for this RT value right there. And then you plug in some specific values, and that's what you get out of it. But what I want you to take away from this is that item right there. Low KEQ, unfavorable. High delta G, unfavorable. High KEQ, favorable. Low delta G, favorable. Okay, now free energy change, or delta G, of any reaction is related to equilibrium, or the ratio of equilibrium and non-equilibrium. So not everything takes place at equilibrium. As we talked about previously, chemists have a different standard state than a biochemist has. In addition to that, a physiologically relevant concentration of a substance is going to be grossly different from that of a chemist's experience. So the physiologically relevant concentration might be very, very low compared to a chemist's standard state. So we're looking at these and we compare them to one another, the delta G versus delta G naught. And we combine it into this equation right here. Delta G is equal to delta G naught plus RT times the natural log of the concentration, these right here being not at equilibrium, or non-equilibrium concentrations. Sorry. Now, free energy change in equilibrium, all reactions proceed until they reach equilibrium. Once a reaction reaches equilibrium, no work can be done. The free energy change of a reaction tells us how much useful work can be accomplished. So if a reaction is at equilibrium and no work can be done, then at equilibrium, delta G equals 0. Now, okay, let me be completely candid with y'all. This is a lot of Gen Chem 2 stuff. If you had a good grasp on Gen Chem 2, fantastic. If you struggled with Gen Chem 2, okay. And I'm not saying okay like in a dismissive manner. I'm saying okay in a way of like, okay, we're going to get through this. The things that we just went over, understanding this graph right here and understanding this concept on the right-hand side is extremely important. So if there's something that you're looking for as a forearm tattoo, this would probably be it. Now, when it comes to biochemistry and delta G values, one of the things one of the places in which it's applied is, I think, a much easier way to understand it. And that is that starting here. So thermodynamic standard state, or thermodynamic state functions, are additive. Now that seems like, okay, I'll accept that. Got it. Makes sense. What those words mean, but I'll listen and I'll hear that sentence. I'll hear that statement. So this is all, and whenever we're studying delta G for this point right now, we're going to be focusing on reaction favorability in the context of metabolism and in the context of glycolysis. So what this means, or another way of phrasing this is, if you have two consecutive reactions, one of them is unfavorable, and the other is favorable. Okay. Combined, these two consecutive reactions might overall be favorable because of how favorable one of the two is. And this idea right here, thermodynamic state functions are additive, that's something that you maybe saw, or you definitely saw when you're in Gen Chem 1 in the context of Hess's law. Does anyone remember Hess's law? Can I get a thumbs up in the chat for yes, I recall Hess's law? Another way of describing, okay, so Hess's law, if you're forgetting it at the moment, it was you had 1, 2, and 3 reactions that would combine into an overall. I'm going to label that as OA. So it'd be like reaction number 1, delta H is -5. Reaction number 2, delta H is 3. And number 3, delta H is -7. And you would rearrange these reactions. You'd say, okay, well, reaction number 3, I got to flip that. So now my flipped reaction has a delta H of 7 as opposed to -7. You'd combine those values and you'd say, oh, well, these 3 things, their overall delta H is going to be 5 because I combined all of their delta H's. So that's my like crash course of crash courses on Hess's law. That is where you've previously seen this idea of thermodynamic state functions are additive. So what you learned as a student in Gen Chem 1 applies here. Now, the free energy of 2 consecutive reactions or a metabolic pathway are additive. So we see this with glucose, which is a sugar that we haven't looked at yet, but we're going to look at next week. Glucose is a 6-carbon sugar. And one of the most important steps in, well, metabolism, in physiology, is adding a PI, or an inorganic phosphate. So an inorganic phosphate looks like this, or it's just a phosphate ion. Adding that to this 6-carbon sugar of glucose, making glucose 6-phosphate. Now, can I get a thumbs up for favorable? That's a thumb right there. Or a thumbs down for this being an unfavorable reaction in the chat. If our delta G is positive 14 kilojoules per mole, is it a favorable or an unfavorable reaction? Thumbs down for, oh, Brendan went with the type thumbs down. Okay, I've got some thumbs down. I like it. You're absolutely right. This is an unfavorable reaction. Okay, so adding phosphate onto glucose is unfavorable. Okay, now let's look at another reaction. Another reaction that is very common in biology and in any sort of reaction, any sort of existence, is this right here, ATP, adenosine triphosphate, which, where is that typically generated in most eukaryotes? There's not an emoji for this, but there should be. The mitochondria, you're absolutely right. That would be a good emoji. It'd kind of look like a little lima bean or something. So ATP, the power is generated in the powerhouse of the cell, the mitochondria. Now, the hydrolysis of ATP, so taking this adenosine triphosphate, this molecule with 3 phosphate groups on it, and breaking it into adenosine diphosphate and 1 inorganic phosphate. So 1 phosphate, breaking that off. We've got a delta G naught of -30 kilojoules per mole. Favorable or unfavorable? Thumbs up for favorable, unfavorable would be thumbs down. You're absolutely right. It's a favorable reaction. So this is unfave and fave. Okay. So these two reactions, one of them's favorable, one of them's unfavorable. they're going to combine together. These two reactions basically are combined into one, an enzymatic reaction where glucose is picked up, as is ATP, and we make glucose 6-phosphate and ADP. Okay, so you can look at this almost right here as being very similar to Hess's law reaction. Because when you think about Hess's law, one of the things that you do is you look at the two reactions or three reactions or however many reactions, and you say, well, something's present on the reactant side and the product side. What do? We cancel it out. Inorganic phosphate is present on both sides of this reaction. That's one way of looking at it. Another way of looking at it is, well, our first reaction has phosphate being added onto glucose. Okay, so then essentially what we're doing is rather than breaking this breaking this ATP into these two things, instead we're removing a phosphate and putting it onto glucose. That overall reaction has a delta G of negative 16 kilojoules per mole. Is that favorable or unfavorable? Thumbs up for favorable. Great. So that is a favorable reaction. Two parts, one unfavorable, one favorable, overall favorable, because these two things are additive. They're combined together to make something that is overall favorable. Another depiction of that with a free energy diagram is shown below, where we've got glucose 6-phosphate or glucose plus glucose 6-phosphate. Glucose plus inorganic phosphate right here. There's an energy barrier to get that phosphate onto glucose 6-phosphate. A positive delta G. Reaction number 2, the hydrolysis of ATP. Oh man, that's a huge drop off. Well, if you combine these two steps into one overall step, the magnitude, the extreme in which to the extreme that reaction number 2 is negative, that offsets how positive reaction number 1 is and gives us something that's kind of nice and in the middle. So this is, I always kind of think about this as like, well, reaction number 1 is 2 steps backwards. Reaction number 2 is 4 steps forward. So where are you? Well, you're net 2 steps ahead, because despite reaction number 1 sending you 2 back, you went 2 forward to offset that, and then 2 more to offset that even further. So that's what reaction number 3 is showing us. And this is like the key part of understanding metabolic pathways, because it's a pathway where enzymes come together to make all of these reactions, whether they're favorable or unfavorable, go in that direction. Now, another example of this is right here. So this is 2 of the reactions in the metabolic pathways for glycolysis are as shown. Fructose 6-phosphate plus ATP leads to fructose 1,6-bisphosphate and ADP plus a proton. Our delta G for this is negative 14.2 kilojoules per mole. Now, this fructose 6-phosphate plus ATP, if we jump back just a minute, that fructose plus ATP is very similar to glucose plus ATP. So these same reactions are taking place. So this reaction, which I'm going to label with a star, is basically identical to what's happening here. These are called phosphorylations. And phosphorylation is the term used for adding a phosphate group onto something. So we've added a phosphate group onto a 6-carbon sugar, fructose being a 6-carbon sugar, which we haven't looked at the structure of that. We will next week. In addition to that, you probably have some some of these sugars are the sugar structures that I want you to know will be sugars that are that you should feel comfortable with, because we're going to focus on the physiologically relevant sugars. There are other sugars, but we're going to focus on the ones of the greatest importance. Fructose, you've probably heard of that because if anyone has had a soda or a sweetened beverage today, they probably had high fructose corn syrup in that as a sweetener. Now, in this class, we won't dive too deep into the potential risks or hazards of that. I'll mention it, but that's you'll get into that a little bit more in metabolism. Now, another reaction here, what we have is fructose 1,6-bisphosphate. This is 6 carbons being broken into 2 different molecules. These 2 different molecules are dihydroxy acetone phosphate. This is a 3-carbon molecule, and glyceraldehyde, three phosphate, which is also, I'm going to circle that 3. This is also a 3-carbon molecule. So this is a reaction where we take a 6-carbon molecule of fructose and split it into 2 3-carbon molecules. These are 2 very important steps in glycolysis. Now, the overall reaction, when we combine these 2 steps, and these are 2 consecutive steps in glycolysis, when we combine them, what we get is something with an overall delta G that it's a little bit less of a burden. And I have to choose these words and speak them carefully, but it's more it's less unfavorable than just this step. These combined steps. Another way of putting it is that when you combine these steps, we make them more favorable in combination. Okay. So these 2 things, like this slide and this slide right here, this portion of the slide, conceptually are very important for understanding metabolism and metabolic pathways as a whole. It's always important to look at the energy of a reaction, because as we will get later on in this semester, we'll get into, okay, well, what's the energy of motion? What's the energy of movement? How much energy is extracted or is needed for me to extend my fingers, for me to bend my arm? How much energy is involved in that? Exactly. Yes, that is another depiction of my Rosetta Stone. So, okay, now this next slide is intended to be intimidating. And it's what we're going to focus on in this class is, or actually, let me take a step back. This right here is a poster that you'll see quite often in biochemistry labs. And this is really just a poster of all central metabolism. So what is involved in production of amino acids, of sugars, and utilization of amino acids and sugars, and how do these different processes, how are they interconnected with one another? Now, in our class and in a metabolism class, what you're going to do is, or in our class, we're going to focus on this right here. And then a little bit, we will focus on this right here. And then, so that's a great question that I got as a private message. Do you learn the whole chart in med school, or is it just for biochemists? I think that it probably depends on your specialization as a physician. Um, and for instance, like if you're a orthopedic surgeon, chances are you're not going to go into consult and say, okay, before we do this to your leg, we got to talk about photosynthesis. I think that there's a lot of practical knowledge that you kind of sift through as a physician. I think that as a physician or PA or any number of different healthcare fields, you do have a pretty good understanding of these things because you do have to take into account, like, how does this drug impact this? Um, I think that you'd probably, let's say as a physician, you probably go here and then you also go here. So this right here is nucleic acids. So DNA and RNA synthesis. And then over here is lipids. But this central channel in the middle is basically sugar metabolism, which is what we're going to focus on. We'll touch on lipids a little bit, but we won't get into nucleic acids or photosynthesis. I think that as a physician, your specialization is going to be very important because if you are, let's say you're an oncologist or something like that, you probably need to have a very strong understanding of nucleic acid metabolism because most chemotherapies, or not most, I'll say many chemotherapies that I know about um, utilize or exploit nucleic acid metabolism because, you know, what they're trying to do is arrest the cell cycle, and nucleic acids are essential for cellular replication. And if you can somehow like derail nucleic acid metabolism by using some sort of inhibitor, then you're in a better place to basically arrest the cell cycle and, you know, kill off the cancer cells. So that's a great question, but to my knowledge, it would be like specialization centric. And same thing for biochemists. Like my background is in plant biochemistry. Down here, this is amino acid metabolism. And I that wasn't a big part of my study. Instead, there's like a whole nother, I guess you would say, chart. There's my, again, Rosetta Stone, with plant hormones, because plants make like 25,000 different hormones. And so that would be kind of where plant biologists and biochemists go. Okay, so this is the slide that I want to introduce, and this is the one that is, here's your overview of glycolysis. I like this figure because it gives you a conceptual overview, I'll say concept, right here on the far left-hand side. And then on the right-hand side, it gives you the names of all of the molecules, the structures of those molecules in the blue column, and then the enzymes are all depicted in this kind of red copper column and this red text here. Now, over the course of this semester, I want you to know glycolysis. I want you to know the structures. I want you to know what molecules come before what molecule. So then when you go on to metabolism, you can just kind of wipe the floor with that. So that you're like, got it, metabolism, done, check. And I think that the more exposure that you get, the better off you are. In addition to that, I think that it makes sense because next week, we're going to talk about this molecule right here, glucose. It's a 6-carbon sugar. And all of these hydroxyl groups, they have specific positions for a reason. And, you know, if I were to take, let's say, this hydroxyl group right here, I'm going to ask you to go with the definition that this hydroxyl group is pointing down. If I were to move that hydroxyl group up here, then it's a different sugar, or it's a different form of glucose. If I were to take this hydroxyl group right here and move it up, then we're not talking about glucose anymore. So what I want you to do, and my ask for this weekend is that you look at this and become a little bit familiar with it. Try to identify, like, do you see any major breakpoints? Like, what happens here? And I'll give you a little bit of a guide there. This is a place where things change. This is also a place where things change. And I want you to kind of familiarize yourself with that. So with that in mind, that's where I'm going to stop my recording. This is slide number 9 of the day 3 PowerPoint. We will pick up from there next week. And I did record this, so I'm going to stop my recording.